right. Thank you everyone for joining us for this MOOC course. So it's the first lecture that we have today on distributed acoustic sensing using fiber optic cables. So I'm Malehmir. I'm course responsible for this MOOC course. And today we're going to kick off. So just before we kick off the course, some practicalities. So the course is being recorded. So we will be sharing the live recording plus the material that we will have. And so I'm a director of this Smart Expression Research Center, and we're organizing this course through the center. So let's get going. So we have 110 registered participants for this course from everywhere, nearly from all continents. And this is a self-paced course, and it's done through a Learning for Professionals, which is an initiative by Swedish government, and we have received funding to run this from Uppsala University, for which we're also grateful. So the intended learning outcome of the course are as following. So as I said, this is self-paced, so you can go through the material later or as you join today. And at the end of all the lectures, which are all given by invitation through various lecturers, we will have a way of assessing your learning. So we will go through fiber optic cable health, splicing them, and this is the lecture we will have today. We will talk about the DAS interrogators, how to extract information from fiber optic cables, whether this is a strain or temperature gradients and changes through the fiber optic cables. And then we will talk about design of surface and borehole fiber optics or DAS applications. And we will likely have some data sharing with you that we will share some scripts so you can work on your own time with the data. And after the assessment, you will also be receiving a certificate. So I just made the certificate today. So a formal certificate, which this would be about 15 to 20 hours of lectures that you have taken, jointly signed by the Center and Uppsala University. So I suggest you to follow us through various places. So as this is sponsored by the center, I would like also to acknowledge the funding. So if you have any questions, you can put them on the QA. You can also reach the teachers. You can, of course, reach me through the email that you have in the first slide. Without any further ado, so we go towards our first lecture, which is given by Grzegorz Paletko, and Greg is our engineer here working with fiber optic cable. So I'm going to make him a co-host right now.
Welcome everyone. That's our first our meeting. Today we will talk about fiber optics maintenance using devices as fusion splicer, microscope, and we can see how this procedure looks like. I am a research engineer on the Department of Earth Science in Uppsala University, and I'm working with the fiber optics, so I can share my knowledge. It will be mostly basically level on the beginning, and I split it, this meeting on two parts. First part will be mostly theoretically about the fiber optics, classification, characterization, some basic knowledge, and second part will be more practically, and we can see some records I performed, how looks maintaining operating with the devices. Let's start. First question: what is fiber optic? Fiber optic, that's a closed structure, is transparent, and the source that we're using for the fiber optics is light, and if we have refraction index then we can keep that light information inside that optical fiber, and instead of the electrical components as copper conducer, we transferring the lights, not the electricity. And the light is mostly emitted here by the LED diode or laser. The story of the fiber optics is quite long. The first phenomena about the reflection waves inside the transparent medium has been discovered in the end of the 19th century, and that idea has been developed, and on the 20th century we had first used the transparent elements that has been used for mostly for medicine, for surgery. These parts that was just some glass bars that has been used for lightning, for the flashing during the surgery, and this was during the 50s, and then some Dutch scientist Bram van Heel demonstrated image transmission with the optical fiber, and that was a milestone step, because from that moment the fiber optic has been started to use as a data transmission, firstly image, and during the Apollo project, NASA used the image on the cameras with the fiber optics first time, and actually that was top secret, and people that used these cameras has been controlled by the government, and in the 80s the fiber optics started to be in commercial use, and has been commercial use mostly for the telecommunication. And from that time, developing this was really fast, because we had technology for improving the material. Material was better and better quality, and data has been sent with the higher speed, with the lower attenuation. And on the 90s, we had a real big boom actually about the fiber optics, because the production has been relatively cheap, and many fiber optics on the ground has been without signal still. And then we started to call these fibers as dark fibers, never used fibers. And fiber optic can be used about 25 years. That's a guarantee of that for that material, and so that was actually not good effect, because we had many unused fiber optics, and we can see here how the data transmission has been developed. It was quite fast. The first record was on 2006, 111 gigabits per second, and now we are in 2023, almost 23 petabits per second. That's a huge difference, and we'll see very soon. Perhaps we will have a optical transfer about exabits. That's a big amount of data, and we can see now how the technology developed with the transmission.
Greg, can you click on these two arrows to enlarge this one?
Yes. Sorry.
Yes, good.
Let's classify how we can classify fiber optics. Actually, fiber optics, that's a part of big group of the waveguides that we can characterized classified by geometry, mode structure, refractive index distribution, or type of material has been used. First, we can maybe maybe no one knows, so many people know about fiber optics that has a planary geometry. That's actually waveguide is used mostly for the biotechnology as biosensors, then where the photons can propagate on the layer, and we can change some parameters, and we can change attenuation. We can manipulate some different parameters as and is not common. It's actually still developing, and the planar waveguide, optical waveguide, is actually is that at least three layers. That's waveguide layer and some substrate on the bottom, and from the top there is the air cover usually. Second type is ribbon, is used for the micro components as optoelectronic sensors, and usually has 12 or more individual fibers aligned in a flat ribbon. So it's just for minimizing size is very common for these micro elements, micro devices, and it can be spliced as well with the different kind of splicer. In one time, we can splice, for example, 12 cores. The most popular fiber shape that we will operate with is a rounded shape fiber optic. The fiber optic has many advantages. Has high bandwidth, is possible to long distance transmission data for the long distance. The fiber optics has immunity for electromagnetic field. That's a big advantage. Yes, and another classification we can see there is two types of the mode transmission in the fiber optics. The biggest difference is the multi-mode fiber optics has a bigger core than single mode fiber optics, and multi-mode fiber optics is mostly used for the shorter distance because it has a quite big attenuation of the data. So that's why we should use the data repeaters even for a roughly short distance, as a few kilometers, because amplitude of the signal dropping very fast. And that fiber optics is used mostly for the distance up to 600 meters. But we can reach quite high speed data transfer with this fiber optics. This fiber optic is much cheaper than single mode. Single mode is the most advanced technique of the fiber optics, and the core is about 9 micrometers, and signal has very low attenuation, about 0.2, 0.35 decibels per kilometer. That's very low. So that's why we don't need to use any repeaters for the long distance. Unfortunately, this fiber optics is very difficult to arrangement and is quite expensive. Another classification, we can see some of the fiber optics has step index, and some of them has a graded index. This is related to used material on the core and on the cladding. For the graded index, the cladding has the core has graduated. The index of the refraction is graduated change. The maximum index is on the middle, and on the side is lower and lower. That's why wave just is reflected gradually. The advantage is the attenuation is lower, and the quality of signal is better, and the higher bandwidth we can reach with that graded index. We can see here that's a schematic of the core of for the graduated index fiber optic. We can see the refraction index is changed very gradually, and is lower on the edge. Then the maximum index is on the middle. That's why wave can be reflected gradually. Of course, that fiber optics are much more expensive. Here we have classification. Depends on the material. The most popular material for the fiber optics is the silica glass. Sometimes it's doped with the germanium or a boron or a fluorine to adjust the refractive index. Here is the picture that I took. This piece of glass fiber is without cladding, is prepared for the splicing. The dimension is about 125 microns, so it's very similar to the dimension of the human hair. And this element has very thermal resist, so that's why that's a big advantage. We can work with up to 350 degree and is resist for the water, solvent, and acids. Is quite flexible, of course, until some point, and because it's very small, we can use many core in the one cable. The plastic fiber optics is very common on the consumer electronic devices. They are very cheap. They have quite big attenuation. We can see in the glass fiber optics we have 0.2, 0.3, and here we have 100 up to 200 decibels per kilometer for the wavelength 650 nanometers. It's used mostly for the connecting electronic devices, audio system or TV system. And we also can see there is two typical material used for this fiber optics is usually polymetal methacrylate or perfluorinated polymers. It depends of our purpose. First one is cheaper. Second one has a better parameters regarding to attenuation, but is more expensive. And third type of the fiber optics is semiconductors. Is made from the fiber optics made from semiconductors. It's used mostly for the very specified purpose as a medicine, military, and laboratory. Is very expensive, and the producing is very difficult. They are I never worked with this kind of fiber optics. but they have very good parameters. That's a big advantage. Structure of the fiber optics. We can see the main structure is the core with the cladding and the coating. These three structures are always exist on the fiber optics, and the cladding that's a material that's covering core, and cladding has lower refraction index. That's why we can keep the wave inside the core. Coating, that's a material made from polymers, and it just adding some strength for the fiber optics. And additionally, we have a strength member that is usually some plastic element. We can have also some additional iron cores, copper elements that adding some strength. We can also have some outer jackets with the additional Kevlar fiber is also adding some strength. But the most important for us is just coating and cladding and core, and these three elements, that's a basic of the fiber optic. Camera. And the typical connectors that we used, there is a lot of standards, but most typical connectors that we can see in our telecommunication industry and DAS technology is SC, LC connector, ST connector, E2000 connector, APC. That's a very advanced connection with the very good parameters. Is used for very often for interrogators, and this connector we will use for our splicing, because our interrogator using this kind of socket. Here we have also female connector, E2000, and here we have termination tip. It's a tip used for terminating the fiber optic. That I will show later. And also LC cable is very common used for the devices. It's only a few type of connections that I wanted to show, but there is many more. Some story about diagnostic. The fiber optics has important parameter is the main parameter of the DAS system is attenuation. That will be Philip for sure will tell more about attenuating and backscattering on the next course. But I wanted just tell a few things about this. The backscattering we can observe when we have not perfect transparent not perfect body of the fiber optics, and then some photons coming back to the beginning, and then we can observe with the interrogator or with the OTDR instrument some attenuation, and the backscattering can be that's one thing, and second thing is also absorption. That absorption is a natural effect for the fiber optics. It depends on the quality of the material that we're using, and we can observe the amplitude of the signal on the end is lower, because the natural absorption for the optical wave exists. Also, when we have banded fiber optics, we can observe some attenuation, and we can see if the layer is very thin, we can observe even the light on the banded or folded part of the fiber optics. And of course, we have all other structural imperfections, and then attenuating exists. Here is example that we can observe that we can use the laser pen for the diagnostic if the signal is transmitted by the cable, and here we can see the light spots. That's an effect of the huge reflection inside the core, is because the core has been broken. And that's why we can observe some reflection, stronger reflection over here, optically with the unarmed eye. And if we will use the OTDR instrument, we can also see some very big attenuation on that part of the fiber optics. That's why mainly OTDR is used, because then we can inspect on what distance we have some issue with our fiber optics, and that can be many things can happen. We can have broken fiber optics. We can have we can have some issue on our connector. We can have some banded part of the fiber optics. This situation increase the attenuation, and that we can observe with the OTDR. For the fiber optic diagnostic, we using the many tools, and these tools that I would like to show you on this course is the fusion splicer, fiber clever that we can cut the fiber. We have to use also heat shrinkable tubing for the covering the spliced parts. We need to use the calibrated, very precisely stripper for the cutting and the coating and the cladding fiber optic. For the diagnostic, if we have a clean connection, we using microscope, because we cannot see in the unarmed eye the core, because it's only 9 micrometers. That's why we have to use microscope. Of course, for the optical diagnostic, we using the laser pen that we can see the laser spot, light on the end. It's very basically stuff for the diagnostic, but it's very useful in some situations, and a very advanced device, OTDR. The clever sharp, that's a very precise element for the cutting fiber optics. If we want to splice the fiber optics, we need to cut the core perfectly in the orthogonal angle. And that's why we using this precise clever with the diamond plate. This device is very sensitive, because even few dust, little dust can de-sharp, maybe not de-sharp the blade, but then we cannot reach the proper angle. That's why it's very important to keep this clever very clean all the time. Is quite difficult, especially on the field work. This element is, beside of fusion splicer, is the most sensitive device. Another another tool very important for us is a calibrated stripper for the fiber optics. This fiber optics stripper is designed for the 125 microns. So we have three steps on this stripper, and first step is used for the coating. Second step is used for the first step is used for the cutting the main body that is mostly usually some isolation outside. The second step is the coating, and the third step is the cladding. And that stripper has a very precise screw that we can adjust this dimension for our radius that we have on our fiber optic. The thermal shrinkable tube is used for the connection that we spliced, because that connection is the cladding and is actually very sensitive and very delicate. We need to add some tube for protection and add some strength for that part. This shrinkable tube has some iron elements through to make it stiff. Here is some picture about our fusion splicer, and fusion splicer does a very advanced device. There is many fusion splicers on the market. There are cheaper, there are more expensive, and that's what that splicer that we used is very advanced splicer. It's totally automatic. It's splicing automatically after adjusting the elements that we put it inside the splicer. The splicer during the splicing checking with the micro cameras if the adjusting of these parts that we cutted are proper, and then there is some electric arc with a very high temperature that's melting these parts of the glass, and then we can observe everything on the display. I will show everything later during the records that I prepared. Here is a microscope that we're using for diagnostic. Some of the connections should be cleaned before we connecting, because can be some dirt or some stuff on them, and then we are doing some additional attenuation, and we cannot observe anything with unarmed eye. That's why we need a microscope with the probe. That microscope that we used. We have some additional adapters for different kind of connectors. And we can observe the middle of the fiber optics, and that black spot looks like eclipse is actually core of our fiber optics, and on that this device connection has been cleaned, so it's perfectly clear. We can see black spot on the white bottom. Here we have some cleaning stuff. There is a many solvents, many pens and box for cleaning that we're using. Many pens has additional adapters designed for the different connectors, and I will show how they can be used later. Here we have some advanced devices, TDR. It's optical time domain reflectometer. The main purpose for this device is just diagnostic the attenuation in our fiber optics that we check, and so we can compare I checked the spliced fiber optic that has been terminated and without termination. The terminated fiber optic has perfectly flat signal, and we can see not terminated properly cable. Even if the connector is correctly spliced, we have a micro reflection inside on the end of the connection, and we can observe some little attenuation. I will show later how we can easily terminate our cable to reach that effect that we want, because for our purpose we don't see any reflection on the end. Here is an example with the cable has been tested by me. Its cable has 1.5 kilometer length, right? And here we can see how signal looks like after 1.5 kilometers. Just signal dropped without any additional attenuation. The attenuation on the beginning is because I used some additional adapter and the cable has been bended. So I had 3 connectors for this adapter. So in these elements, we had additional reflection. That's why we have some attenuation peak on the beginning. We have to check. We have to know the fiber optics has many hazards, because when we operating with the fiber optics, actually has a very micro. It's a very micro element actually, and the thickness is similar to human hairs. So, and because it's very stiff, it can easily be put it inside accidentally to our skin, and we can also accidentally touch our eyes with the fingers that we have a piece of the fiber glass elements. It's very dangerous. That's why we should add some precautions. We should use the proper glass, the gloves when we splicing, and also during the diagnostic we have to be careful, because diagnostic is very often with the laser lights. So we have to be sure that the laser light don't coming out on the cable. We should be sure that the source of the laser is off to be safe with this. Also, chemical hazards. The splicing is used very often with some additional solvents for cleaning, as isopropyl alcohol, epoxy mass for adding some strength. Many substances depends of our our maintenance. We should do some precautions. We should check the safety data sheet of this material that we're using. It's very important. And the splicing environment that we work with should be clean, should be ventilated well. We have to be sure there is not a third person that can be accidentally involved to that situation when we have some piece of glasses on the table or somewhere. It's very important to keep it, and also the laser detectors and the source should be used with the big precautions. That's a very shortcut about the fiber optics, the hazards, and the safety practices. I would like to show now some practical records from the practical aspects, how we can use these devices, how we can splice, how we can check if the fiber optic connection is correct. Let's see. So maybe I will close that. Of course, after all, we will have some time for the questions, for the discussion. Let's see movies about the splicing. Okay. Full screen. Okay. Here we have Here we have a splicer that we are operating with. That's a center splicer, and it's a big display inside. Inside of the splicer, we have some electrode and lockers that we putting inside our fiber optics. Yes, here we have also micro cameras. That cassette that I'm opening, it's a port for the heating our shrinkable heat tube, and the main cover should be closed always because these elements inside are very sensitive. Here we have our fiber clever. It's a very precise device with the diamond shape, with the magnet locker for the fiber optics. It's very sensitive, and another view for the elements inside the splicer. That's a main electrode that we have. Here is a micro camera that we can observe our fiber optics. Here's a port that we put in our spliced element that we want to splice, and yes, here the clever. Here we have a blade that is very sensitive, and here is the port that's locking our fiber optic inside. That's a fiber optic decoating with the cladding, and we will put the fiber optic inside this clever. Here also we can see isopropyl alcohol we will be using for the cleaning, stripper for the cutting, and the cladding fiber optics. Yes. Another view. Here we have electrode that we have electrical spark, and here we melted the fiber optic. Here is our fiber optic cladded steel, and we will use this stripper for the cladding. Here is fiber optic decladded already. We can see some decladded material, and here is our glass. And that glass looks clean, but when we check closely, this glass element is still dirty. We can see here. We cannot put this glass into our clever. We have to use the solvents, for example, isopropyl alcohol, and we can clean this glass. Actually, I used one hand. That's why it's because I hold the camera in one hand. That's why not seen so clear how I'm cleaning, but it's very quick operation, and now we can see. Yes, and now we can see this fiber, this glass. This glass is clean now. It's very difficult to focus on that small element. Yes, we can see it's almost transparent, and that prepared glass fiber we can install in our clever. And this clever has a magnet. Yes, here is a better view. We can see is clean now. And this fiber optics we are installing in our clever. We have field signate for these elements, and lockers are magnetic, and the cutting is with only one push, and we can see the glass is cutted. Here is a piece of the glass cut it off, and that fiber, if we have clever with that works fine, should be cut perfectly in the orthogonal angle. And second step is just installing this fiber optics, this cutted fiber optic in our splicer. The tip of that cutted edge should be next to the electrode, right next to, and this locker is magnetic, so holds quite strongly this fiber optic. And second part of the fiber optic that we want to splice with, the first has to add some shrinkable tube, and we repeating operation with the cladding. And the very important thing is we have to remove our cutted off piece of the glass. I'm using very often the duct tape or some strong tape for the just sticking this piece, because it can be flying away somewhere, or we can accidentally touch and put it to our skin. We have to be very careful about this piece. We actually should count how many piece of glasses we should have after cutting, because we can have very big problem to recognize later if we have something on our hands or pants or whatever. We should be very worried about this. And here is another edge, another fiber optics cut it already, and we are installing next to the electrode. That's a properly installed fiber optics right before the splicing. If we close our splicer, all operation will be automatically done. The micro cameras checking and adjust the micro mechanism, adjusting the position of the fiber optic inside. And if everything is proper, the splicing is done with the 1 second. And we have results. The attenuation of our connection is very good, 0.01 decibel. That's a quite good result. And now splicer checking the tension force, because the connection should be tested. And after that, we have to set our shrinkable tube on the right position, because that connection is very sensitive. And here in that heating port, we're just waiting for the moment when until the heating will be done. And after all, we have done our connections, and that's not the end of the work, because now we should test our connection with the laser of OTDR. Now I showed some typically used connections. That's a E2000 connector that we're using. Here I'm showing the laser pen. That's a very simple device for diagnostic. Here is a microscope with different adapters that we're using for the diagnostic our connection, if it's cleaned well. And different adapters are used for different connectors. Now we have a connector adapter for E2000 connector, and that probe can be that probe has regulated contrast that we have to adjust, and now we can observe on the display the image of the core that we cannot see without microscope. We can see some spots on the device screen, so we can expect that connector has been used before, and we should clean it a bit for the next operation. This is cleaned very well how the code looks like. That's a cleaning pen, and this pen has adapters for the E2000 connector, and this pen is very often used for these connectors because we can very easily and quickly clear this core on that connector, and the adapter is designed for this connector. For that's no problem for using this. We have to click and rotate, and we can check again if that cleaning has been done properly. As we can see now, the core looks much better. There's no any spots on the device, on the screen device. So the cleaning has been good, has been done well. Here I used different adapter for different connector. Yes, here also we could observe the core. You can see the core. We can use the cleaning box for cleaning this connector tip. And after I cleaned, I showed what's happening if we accidentally touch our skin, how the core looks. And now we can see how it looks. That cannot be used, of course, by us, and we cannot connect this kind of thing. We have to check with the microscope always if we want to be sure if our connector is prepared for connecting the device. For example, as sensitive as interrogator, we have to clean everything perfectly. And that's why we're using the microscope. That's I'm just showing the adapters that we're using. That's one of the most advanced device that we're using. That's OTDR. OTDR is OTDR only. That's one functional of that device, because we can also use it as microscope, as FL. So we just can use as a laser pen. But we will focus mainly on the OTDR function. And that device has 2 ports for single mode cable, for multi-mode cable with the different range of the wavelength. And we can check our cable. For that purpose, we have to add some additional adapter I prepared. because that device doesn't have E2000 socket, so I'm using the cable, additional cable, and that E2000 is connected with the adapter. And now we have connected the fiber optic or the TDR. This fiber optic is about 30 meters long, and here we have additional 1 meter length, about 1 meter long adapter cable. And when we set our wavelength, we just pressing the testing mode, and we can see first attenuation on the beginning because we have adapter cable, and second big attenuation, and that big attenuation is very big, so we can expect we have some issues on our cable. And when we checked with the laser, we see the cable has broken parts right before the connection. There is a huge reflect inside, and there is not any lights outside. So for that example, we can see how laser pen can be used. Yes, we should see the laser. We don't see anything. The signal going only for that moment. And here I prepared some instruction how we can repair that cable from A to Z. And here we have tools that we will use: the stripper, the clever, splicer, and that view is from the top, so we can observe how everything looks. We should cut off the broken parts. We should remove the outer layer with the coating, with the additional Kevlar fibers that we have to cut off. And in that prepared the cable can be decoated. We decoated with the stripper, and now we have fiber optic with only ladder, and with the cladding the fiber optics with the stripper. There's cladding material, you can see. Now we will use a bit of the isopropyl alcohol for the cleaning. If the cable is cleaned, we can install it in the clever. And to do that, we have to do that very precisely, and the cutting is very quick, only one movement, and that cutted cable is ready for the splicing. We can prepare our splicer now, and we can install the first fiber optic that we will splicing. These lockers are magnetic. Now we have a second part of the fiber optic that we want to splice with. The first one, we have to add the shrinkable tube. Of course, we cannot forget about this. First step, the coating. And now the cladding. The cladding does a very thin layer, and sometimes sometimes we can think, oh, it's almost our core, but if we will use this stripper, we can move, and we can move on and on that part of the cable, and we can see there is a lot of material that is used for layering these elements. And now we have a clear glass that we installing in our lever. We have to remove that cutted off piece of the glass for our safety. So we cutting the second, and we install the second part of the cable. If we are sure the cable is properly installed, we can observe the display on our splicer. The micro cameras observe and adjusting the fiber position, and if everything is correct, everything is done automatically. We can see the result 0.01. It's very good result. And now the micro mechanism testing tension force. And we can prepare the heating slot. And that movement is very important because this part of the element that we spliced is very sensitive. We have to be very delicate. And that's prepared. The cable can be put into the heating slot, and the heating has been started. We can see the diode inform us about the heating process. We can close the splicer. We should close the splicer because we cannot allow the anode to get in because all these mechanisms is very sensitive. After heating, we have proper connection. That connection we can isolate with some isolation. Additionally, we can add some additional shrinkable tube for making it more strong. And we should test our connection with the laser pen. We can do that very quick. We connecting everything, and we should observe after connection. We should observe the light spot on the end. That's our first thing that we can expect that the work has been done properly. But we have to do also diagnostic regarding to attenuation. We have to check if our cable has low attenuation in that part that we spliced. And we can observe, yes, this cable is done properly. We have low attenuation. Low attenuation over here is because we have not terminated cable. We have just connector on the end. So we have some additional reflection. When we terminate the cable, we can do that very easily with the female connector and the termination tip. The optical signal is absorbed properly without any reflections, and we can see then the cable has a proper signal on the end. And that's way that we should always terminating our cable when we're using the DAS system. And yes, we can manipulate this chart on the screen. We can export this as the file or as the PDF file. We can save the data. This device has many functions. We can also do tests for different two different wavelengths. And here is showed very quick how we can extract the fiber optics from the typical cable that we're using in the ground. We need some scalpels, and this maintenance take a time, because very often we have some additional layers. We have some additional Kevlar fibers. We have some additional plastic material. After cutting off this plastic material, we can see we have to do everything very carefully, because we don't want to break our fiber inside. And we can see there is many cores inside. And the cables has 4 cores, 8 cores, 12 cores, depends on the cable manufacturer. And these cores, these fibers are layered with additional substance that is blocking the water going inside. And we have to clean everything and remove this substance. And we can see here we have a course. And now we have to select proper one, and we have to do decladding and splicing again with our cable. You can see that's almost surgical operation, and everything is fine when we have a very nice environment in the laboratory. But the more problematic situation is if we have some field work, and we have to do that on the outside during the not good weather condition. Yeah, the patient is most important thing during the splicing the fiber optics. And here is a prepared connection. It's isolated outside. And here we have fiber optics going to that's a connection that we can use for our interrogator. That was a shortcut about this maintaining with the fiber optics.
Greg, thank you very much. Very useful lecture. I have very much learned myself. You got one question at least here, and I think we can open the floor now for question. You can just raise your hand, and I can give you access. So you got the first question on the last set of fiber cable. Were all the colored cables fiber, or was it only the white one coated fiber?
Let's see. Which?
I think it was the last set of cable. I think they were all
yes. The producers used the different colors for the different cores, because then we can easily select proper channel, and every producer adding some data sheet about the fiber optics, and there is a specified which core is, for example, single mode, which core is multi-mode. Or there is also some color codes, so we are sure the blue color, that's a first channel, and that's a single mode. The brown color, that's a multi-mode channel, and the color code is used always. when we have some commercial cable that has more than one core inside, and usually we have at least 4 cores inside or more. So colors are always used, and the first channel is very often just a blue color. And this cable that I spliced, that was just fiber for the connector, so it was single cable, so that's why it was blue. That's why it was white, and the cable has usually yellow coating because it's more visible.
Are there more questions in the live session from here? All right. If there are no questions, thank you, Greg, for
We have something.
I'm curious about you. You read it?
Yes, I'm reading. Could you share a link? Okay, so I see some question about termination cable. So this tip that I used for terminating is tip designed by E2000 standard, and this tip is the construction of this tip is designed for the terminating. I haven't used different kind of termination, but I know there is many options. But I'm using the E2000 connector for our dust instruments, so that's why I always terminated with only E2000 tip. But you can compare easily the connection without terminating, with terminating, and if we have broken or cut it off cable, then we have cut it off cable, then we have a very big attenuation, and of course the signal doesn't propagate through. So that's why we can easily recognize.
But maybe a question from me. Have you compared using the tip terminator with like nothing?
The tip terminator, that's our best choice, because we have zero attenuation. Every kind of different method that I used, as noting, as gluing, as adding some different tip, adding some reflections, so we can see at least some small peak of attenuation on the end. Of course, it's not big problematic, I think, during the measurement, but we want to reduce the attenuation up to 0 totally. We can use this kind of tip. Of course, there is many different standards, but I haven't used, so I cannot say anything.
Thank you very much for being part of this lecture today.
Thank you.
Bye-bye.